Hello everybody, and welcome to the first episode of a new series that we're going to be doing here on physical attraction called Climate 201. So in this show we're going to attempt to explain some issues surrounding climate change in a bit greater depth than we've done so far. This is my area of expertise if I have one, and I've noticed that the debate surrounding climate change, especially on climate Twitter, it can get extremely complicated. Before too long we're using all these obscure acronyms: ECS, BECS, RCPs, GCMs, ESMs, IAMs. And the whole procedure, the whole debate becomes extremely technical and specialist. But I know that there are lots of people around the world who would be fascinated to learn more about climate change, specifically the solutions, the practical actions that we can take to help resolve this problem. And when they see claims in the media, they want to feel like they have the critical faculties to evaluate them, and they want to decide what they should do in their own personal lives to be most effective at solving this problem. And of course, you want to understand it because you want to better understand one of the great trends and historical forces that's really going to dominate this coming century and affect all of our lives over the next few decades. I think sadly for many years, a lot of the conventional media coverage of climate change has been overly simplistic. It was just a few years ago that the media finally decided to move on from the long ago solved question of is it happening or not, to the far more fascinating and complex question of what can and should we do about it. But even in this later phase, where much of the media is now focusing on what can be done or what should be done, we're still seeing that things are done in this very simplistic way where every headline is, we have 12 years to fix the problem, we have 6 years to fix the problem, we have 5 years to fix the problem, the Paris Agreement is in trouble, and so forth. And there's not a great deal of analysis as to why this is happening, which sectors can contribute, what the technologies are that are being assessed, and which actions government should be taking and corporations should be taking. And really in-depth analysis is missing from this sort of overly simplistic picture of, oh, the end of the world is nigh, that you get a lot of the time when you're talking about popular perceptions of climate change. So this is really Climate 201, where I want to bring some of the complexities, shine a light on them and explain them in more detail, tackling each issue at a time. And it's going to take us across a range of things: scientific, political, social or economic. And I'm going to try and explain enough of the thinking about it so that you can get up to speed with the real climate debate that's going on at the moment. And I'm aware that I don't want to take over this show entirely and turn it into a completely climate change show. So this is going to be, we'll release a few of these episodes at a time and then perhaps have a break, go back to our sort of more regular content and then release a few more. So it's going to be something that runs in parallel alongside what we've been doing so far, kind of like interview episodes or news episodes have been so far. So I hope that people find this series interesting. The first thing that we're going to start off with then is, what's a greenhouse gas? Greenhouse gases are pretty much any gas that can undergo the greenhouse effect. Now, the idea in physics terms is pretty simple. Every object with a temperature is emitting radiation of some kind. You can imagine temperature as expressing the energy available in molecules in terms of their vibrations or movement. In fact, the average energy that's available to a molecule in a gas is proportional to the Boltzmann constant multiplied by its temperature, although some molecules within that spectrum will be vibrating more quickly while others will be vibrating more slowly. Very approximately speaking, when objects emit radiation because of their temperature, it's in the form of what's called a blackbody spectrum. Now, the blackbody spectrum depends on temperature, and it emits across a range of different wavelengths of light or electromagnetic radiation, which depend on the energy that an object has. And everyone's familiar with classic examples of this in real life. If you heat an object, say a poker, at first it goes red hot. If you heat it higher, it goes white hot. You can see similar things in stars, where the brightest are blue, the dimmest are a sort of faint red colour. You can understand this by imagining the spectrum, the shape of which, this blackbody spectrum, is called the Planck spectrum if you want to look up what this graph actually looks like. And at higher temperatures, and as the object is heated up and becomes more energetic, this spectrum is shifting towards higher and higher frequencies and shorter wavelengths. So at lower temperatures, the peak of the spectrum is at the low energy red part of the visible spectrum. So the object is emitting radiation at frequencies that we can't see, such as infrared. As you increase the temperature, the peak of the spectrum shifts to cover more and more of that visible spectrum until it's strongly emitting every colour at once. So you move through something that's glowing red to getting to white hot. So this procedure is really familiar to all of us. So now if you consider a really simple system of the Earth and the Sun, and you have to remember a key thing about physics here: simple models are wrong because they miss out details, but by capturing the spirit of what's going on, they can help us to understand it. The Sun's surface temperature is about 5,800 Kelvin, 5,500 degrees Celsius, and it irradiates the Earth with higher frequency light in the visible and UV spectrum mostly. Now, because the Earth is millions of miles away from the Sun, only a fraction of that solar energy is absorbed by the Earth. If you imagine it spreading out over a sphere from the Sun to where that sphere would intersect the surface of the Earth, you can see that we're only going to absorb a tiny fraction of it, because we only cover a tiny fraction of the sky relative to the Sun. Now, the laws of thermodynamics illustrate that over time, if there's no external influence, no changing energy supply, things tend towards a thermodynamic equilibrium, so a changing, unconstant temperature. Now, the Earth as a whole, very approximately in this model, is going to be in thermodynamic equilibrium. And because the Earth as a whole is surrounded by space where there's virtually no matter at all, it can't transmit a lot of heat through conduction and convection, unlike when you touch a hot object and its vibrating molecules pass heat into your hand. So the only choice for the Earth as a whole is to absorb and emit radiation to come into thermodynamic equilibrium. So it's in what we would call radiative equilibrium, because the only way that energy can get in is radiation from the Sun and other stars, and the only way it can leave, really, is radiation from the Earth's surface out into space. We know that the total energy an object radiates is roughly proportional to its temperature to the power of 4. This is an approximation, but it works pretty well for most objects. Consequently, if the Earth is exposed to solar radiation, it's going to heat up until its temperature is high enough that it's radiating away the same amount of energy that it's absorbing from the Sun. Now you can use this, plus the distance from the Sun to the Earth, to figure out an approximate temperature. And if you do this, crudely taking into account the reflectivity of the Earth's surface to determine the energy that would be absorbed, you find that the Earth's temperature would be around minus 18 degrees Celsius on average. Now, we know that the Earth's temperature is not minus 18 degrees Celsius on average. As I'm recording this episode right now, we're going through one of the hottest days in memory in Britain, which is probably leading to some considerable distraction while I'm trying to narrate this. It's obviously not minus 18 degrees Celsius on average. It's actually around 15 degrees Celsius on average. Both of those figures are from NASA's Goddard Institute for Space Sciences. And part of the reason for the difference is the greenhouse effect. Effectively, greenhouse gases in the Earth's atmosphere have molecules that can interact with radiation. The Earth is heated by solar radiation from space, and it balances this by emitting infrared radiation from its surface. That radiation is absorbed by certain gases, those which have energy levels that correspond to the spectrum of energy emitted by the Earth. When they re-emit, they emit the radiation in randomized directions, which means that some of it is emitted back down to Earth and effectively can't escape. And that is absorbed by the Earth and it heats the Earth more. So in other words, having these greenhouse gases in the Earth's atmosphere mean that it is less effective at emitting radiation to space. To compensate for this, the Earth has to heat up. As it heats up, the total energy that it's emitting is going up by this sort of T to the 4 power, and so it's emitting more radiation to space. And even though some of it is being absorbed, it can now overcome that to be back in radiative equilibrium again. But obviously the more greenhouse gases you put into the atmosphere, the more the surface of the Earth is going to have to heat up to compensate for the fact that part of this radiation that it would usually emit to space is now being absorbed. Now you can tell that this effect is going on by looking at the radiation that Earth emits from space. So this is the outgoing long-wave radiation. Now what we would expect to see if there were no greenhouse gases at all is we could stick a satellite up into space, we could look at the frequencies of the radiation coming from Earth, and we would expect to be able to plot Earth's blackbody radiation spectrum. And we could say, okay, Earth has an average temperature of about 15 Celsius, this is what the spectrum should look like. If you actually observe it from outer space, then you can see that it looks a lot like the blackbody radiation spectrum, but with big bites taken out of it. And these bites are where radiation of certain frequencies can't escape nearly as much. It's attenuated. It's a little bit like if you were looking at a white light with a certain filter on that was preventing the blue from getting through. That's essentially what's happening in the Earth's atmosphere, seen from space. And you can look at these individual notches, and you will see that these exact notches correspond to the known energy levels in given molecules. And of course we can study these molecules in the lab. You can figure out the energy levels and the absorption spectra and the emission spectra of things like CO2 or ozone or water vapour. Just by studying them in the lab and shining lights through them, that's all you have to do. You can figure those things out. And by observing which frequencies of light they can absorb and emit, we can determine exactly what we'd expect them to do in Earth's atmosphere, and then we can actually observe this effect through satellite data. So this is why it's kind of very irritating to get climate quote-unquote skeptics or deniers who say that this isn't happening, because not only is it extremely well established that greenhouse gases are acting to heat the Earth beyond what incoming solar radiation would do alone, not only can we actually go into space and look through satellites and see that this is happening and that these precise chunks of the radiation spectrum are being taken out by these gases. But also, if this wasn't happening at all, if the greenhouse effect didn't exist or didn't influence climate, then Earth would be about 33 degrees Celsius colder and likely totally inhospitable for human life. Now, the dominant greenhouse gas in Earth's atmosphere is water vapour. This is what contributes the vast majority of that 33 degrees Celsius temperature increase from the Earth's natural radiative temperature to the actual temperature of the Earth. Now, human activities don't directly do a huge amount to increase the amount of water vapour in the atmosphere. Water vapour cycles through the atmosphere very quickly. We call this rain. However, water vapour's greenhouse effect does contribute to climate change because it acts as an amplification effect for what we do. So first, if we increase the concentration of CO2 in the atmosphere, that increases the temperature of the atmosphere, which allows the atmosphere to hold more water vapour, which leads to this feedback effect that's going on. And the feedback effect amplifies the direct effect of warming by greenhouse gases by between 2 or 3 times, depending on which factors you include and how your model works. So anthropogenic climate change arises due to the addition of additional greenhouse gases that we're adding to the atmosphere. Perhaps too often this is expressed as being completely synonymous with carbon dioxide. Carbon emissions are what we focus on. But of course there are many other greenhouse gases that humans either emit or have some influence on emitting that absorb at different parts of the spectrum. Now there are 2 main reasons that the discourse predominantly focuses on carbon dioxide. The first is that in terms of the impact that our emissions have, it's the largest contributor. For example, if you go back to 2011 when the IPCC did their big AR5 report, you can see that the effects of different pollutants emitted by humans, in terms of their impact on the radiative forcing of the climate, they have a graph which looks at all of the different effects of these pollutants. For example, if we go back to 2011, we can look at the IPCC's AR5 report. In this report, they look at the effects that different pollutants have in terms of their impact on the radiative forcing of the climate. So, in other words, the radiative forcing of the climate is the amount of energy that the greenhouse gases, for example, are trapping per unit area. Or alternatively, if it's something reflecting energy, it's the amount of energy that's reflected out of the Earth system per unit area. So it's expressed in watts per square metre. That is to say, it's a power, it's an energy that's being reflected or prevented from escaping. And that's the positive or negative radiative forcing of the Earth system. In terms of radiative forcing then, the radiative forcing due to CO2 back in 2011 was 1.7 watts per square metre. The next highest contributor was methane at 0.97 watts per square metre, then halocarbons at 0.18 watts per square metre, then nitrogen dioxide at 0.17 watts per square metre. There are also some negative contributions from aerosols and from the cloud adjustment to aerosols, but we're just focusing on the positive contributions from greenhouse gases today, so we'll leave these alone for now, pausing only to note that they do partially compensate for the warming due to greenhouse gases. So you can see that CO2 is around twice as large in impact as its next biggest competitor, methane. But as we'll discuss later, directly comparing these 2 gases purely on radiative forcing terms can be misleading. Because the other reason that CO2 is focused on is that it lasts in the atmosphere for the longest time. Some of the CO2 emissions from today will remain in the atmosphere for thousands of years. Again, according to the IPCC's 4th assessment report, about 50% of a CO2 increase will be removed from the atmosphere within 30 years. A further 30% will be removed within a few centuries. The remaining 20% may stay in the atmosphere for many thousands of years. About 50% of a CO2 increase will be removed from the atmosphere within about 30 years. The further 30% will be removed within a few centuries, and the remaining 20% may stay in the atmosphere for many thousands of years. So it's this long-lived impact of some of the emissions that we're throwing up today that is a big part of why carbon dioxide is the main focus. But I want to have a look at some of these other climate pollutants as well. Methane has a natural cycle, just like carbon, where it's put into the atmosphere by certain natural processes and removed as well. But in recent years, methane emissions have increasingly been dominated by processes influenced by humans. We're talking about cows and other grazing animals that emit methane, both directly from their digestive processes, where the microbes that help them break down grasses actually produce that methane as a byproduct, and also in their manure, where these microbes again are feasting on the manure and releasing methane. So between those 2 things, the agriculture, herd animals account for about 40% of human-influenced methane. But there are also methane emissions from rice paddies. When they flood, microbes break down the rice and they also emit methane. And an increasingly large contributor is fugitive emissions from the gas and oil sector. We have oil wells, natural gas pipelines, coal and so on. All of these production processes, methane leaks can occur. And that probably accounts for at least 25% of the human-caused emissions of methane. Now, there are indications that this figure is rising as the world increasingly shifts from using coal to using natural gas, where leaky pipelines are responsible for substantial methane emissions. As the demand for meat and beef particularly increases, and the use of natural gas also increases, anthropogenic methane emissions are generally rising year on year, and they have done in the last few years. Crucially though, methane only has a lifetime in the atmosphere of around 12 years, before typically decaying into CO2 and water vapour by interacting with oxygen hydroxide, the hydroxyl radical in the atmosphere. Crucially, methane only has a lifetime in the atmosphere of around 12 years before typically decaying into CO2 and water vapour by interacting with the hydroxyl radical, that's OH- in the atmosphere. There's not much OH- around, but occasionally a methane molecule bumps into this, they interact, and you get CO2 and H2O out of that. We'll come on to this a little bit more later. Thinking of some of the others, we have nitrous oxide, N2O. This is one of the more long-lived greenhouse gases, with a lifetime in the atmosphere of around 120 years. And it's emitted primarily due to the application of nitrogen-heavy fertilisers in agriculture, and also in the procedures that make those fertilisers. In the US, around 82% of nitrous oxide emissions come from agriculture or manure, while the rest comes from various different fuels being burned in transportation and industrial processes and so on. In the US, again, the trend for these emissions is pretty flat. But the use of nitrogen fertilisers is a really difficult thing to wean ourselves off. It's a huge part of what allowed us to produce as much food as we do today. Those of you who listened to the Teotwalki specials way back will remember when we talked about the Malthusian catastrophe, and actually it was the Green Revolution and the application of things like fertilisers and monoculture cultivation and so on that actually allowed us to produce the food levels that we do to sustain the population that we have today that meant that Malthus was wrong. So these emissions are difficult to eliminate entirely. However, there are approaches to agriculture and soil management that involve using nitrogen much more sparingly and efficiently, which can at least minimise these emissions. There are additional greenhouse gases to consider, including so-called F-gases or fluorinated gases. These are gases with fluorine in them, as the name would suggest, which includes CFCs and HFCs. These are typically used for refrigeration, and they can last in the atmosphere for centuries. CFCs are of course more famous for helping to deplete the ozone layer, which we covered back in the episode Climate Change Lessons from Montreal. That episode attempted to explain why it was that humanity had done a relatively decent job at fixing the hole in the ozone layer once it was discovered, and why climate change is a much more difficult problem to solve. Under the Montreal Protocol, CFCs are banned, but their replacements, HFCs, which do not deplete the ozone layer, are not yet subject to a global ban. So these HFCs, the hydrofluorocarbons, are the most common F-gases in use today. They're used in a multitude of different applications: commercial refrigeration, industrial refrigeration, air conditioning systems, heat pump equipment, and as blowing agents for foam, fire extinguishers, aerosol propellants, solvents, this sort of thing. Perfluorocarbons, or PFCs, consist of fluorine and carbon. They're used in electronics, cosmetics, pharmaceutical industries, as well as in refrigeration combined with other gases. There's also SF6, which is sulfur hexafluoride, and that's primarily used as an insulation gas. You can actually find this in high voltage switchgear, so in your electrical power grid you get some SF6 emissions coming from that. And it's also made in the production of magnesium. So all of these F-gases are relatively small contributors to global warming, and they're produced in relatively small quantities compared to CO2 or methane. But it should be pointed out that, molecule for molecule, non-CO2 greenhouse gases do result in much more warming than CO2 does per molecule. There are a couple of reasons for this. Firstly, we have to consider the molecular structure of the greenhouse gases. Generally, more complex molecules have more energy levels, and these energy levels will be at different parts of the Earth's infrared spectrum. So typically you need to consider which gases are going to take a nice big chunk out of the Earth's blackbody infrared radiation emissions to space, based on where the molecule's energy levels are, and how they line up with what the Earth would naturally emit. Secondly, and more importantly, you need to consider how much of the gas already exists in the Earth's atmosphere. As explained, these molecules can only absorb part of the Earth's outgoing radiation, depending on their energy levels. This means that as the atmosphere contains more and more of a particular greenhouse gas, it becomes more and more opaque to the given frequencies of infrared radiation being emitted from the Earth's surface. But this in turn means that each new molecule you add is going to be less effective at trapping radiation. One way to imagine this is by considering the atmosphere as layers of these molecules. Let's say a layer of a certain thickness, T, can cut transmission by 50%. This is obviously an oversimplification and not what physically happens, but it's just an analogy. So if we inject enough of our gas to form a layer of thickness T, then we know that we'll cut the infrared radiation transmitted through the layer by 50%. If we add another layer of thickness T, we'll cut the transmission by a further 50%. But since only half the light made it through the first layer, cutting that half in half means that 25% of the original light has made it through both layers. In other words, adding the second layer has just cut down on the original light transmission by 25%. If you added another layer, it would only reduce the original light by 12.5% of its initial energy, and so on. So effectively, as you're taking a bigger and bigger chunk out of the Earth's infrared spectrum, you're getting less and less effective as you do it, you're getting closer and closer to blocking out all of the light, and throwing up more of your greenhouse gas eventually is going to saturate and stop having the same effect that it would have done if it was the first molecule there. And this is similar to what happens in the atmosphere. The radiative forcing depends on the logarithm, the inverse exponential, of the concentration of gas. So each doubling of the concentration will increase the radiative forcing by the same amount. You can imagine this as the atmosphere becoming more and more opaque to certain frequencies as the concentration of gas increases. And again, if you think about a light source, you're putting layers and layers of red filter in front of it. Eventually, you'll have put so many layers of red filter in front of it that you've blocked out all the red light. But then a single blue filter will do far more to dim the light that's getting through altogether than adding more and more red filters. That's why, pound for pound, so to speak, injecting a molecule of CO2 into the atmosphere has much less impact on warming than a single molecule of HFC12. HFC12 is a much rarer gas in the atmosphere. By some metrics, each molecule of HFC12 is worth between 1,000 and 3,000 molecules of CO2. But since we emit billions of tons of CO2 a year and far less of HFC12, it's a much less important component of our total forcing of the climate system, our total contribution to anthropogenic climate change. Even though, pound for pound, it's obviously a very powerful greenhouse gas. So now we have enough background to start to explain some different terminology and introduce some of the active debates in the climate change space. Because the problem you'll likely be identifying here is that all the greenhouse gases have different properties. They warm the climate by different amounts, they have different lifetimes in the atmosphere, and there are different ways that we can hope to mitigate them. The issue is that you'll face endless problems in setting climate policy, both directly and indirectly, where you will try and compare the effects of different greenhouse gases. And the issue here is one of fungibility. That is to say, can we set an exchange rate and say that 1 tonne of methane is really worth 3 tonnes of carbon dioxide? Can you happily get a single number that will compare the emissions of different gases to each other in a meaningful way? Or are you not able to compare them in this way and you have to consider and compare them all as individual gases? Well, that can get very complicated. To illustrate, there are plenty of places where you're going to want to do this. Take switching from coal to natural gas. This will decrease your CO2 emissions. Natural gas, when burned, produces half the CO2 of coal, which, along with the expense of coal, is why the world is increasingly shifting from coal to natural gas when they use fossil fuels at all. But it's also going to increase your methane emissions from leaks in the pipeline that transport that natural gas around. So how do you account for this? You're making a decision which increases methane and decreases CO2. Of course, you have to account for a couple of different things, the different lifetimes of gases in the atmosphere, and the different warming potential that they have. As we've mentioned, a single molecule of methane is much more effective at trapping heat than CO2, but it decays much more quickly in the atmosphere. So if we want to compare the different greenhouse gases, we need to find some way to take that into account. Typically, the approach from science has been to try and create different metrics that allow you to compare the different greenhouse gases. And these metrics have to depend on the timescale over which you're concerned about the warming. For example, methane clearly has much more short-term impact on warming, pound for pound. For the first 12 years, much of it will still exist in the atmosphere as methane, and so the fact that it's more effective at heating is more important. Over the longer term, though, more of that methane will have decayed into CO2. 100 years after you emit a ton of methane into the atmosphere, the warming impact that it will have then will basically be quite close to that of a ton of CO2 that was emitted. So in the long term, methane is not that much worse than CO2, kilogram for kilogram, so to speak. And this is further complicated because, of course, all of this is technically time dependent. By the time your methane decays into CO2, the CO2 and methane concentrations will be different, and so the changes to radiative forcing you'll get will also be different, although that's really a second order effect. So to untangle this, scientists typically look at a time frame. We need to integrate the effects of the different molecules over time so we can take into account how they're changing, and how much warming is contributed in that time frame. This is done using global warming potential, or GWP. Typically, when GWP is specified, it's over a time frame of the next 100 years, but it can also sometimes be calculated as GWP over the next 30 or 20 years. So, for example, in terms of warming over the next 20 years, taking into account the decay of methane into CO2, a single molecule of methane contributes around 85 times the warming of a molecule of CO2. Over the next 100 years, though, it will contribute around 32 times the warming of a CO2 on average. And the reason for that is because for the last 70 years of those 100 years, you don't have as much methane around. So these global warming potentials provide a kind of exchange rate where we can say that, integrated over 100 years, one molecule of methane warms 32 times more than CO2, one molecule of nitrous oxide warms 280 times more than CO2, and one molecule of CF4 warms 7,000 times more than CO2, and so on. Some people will then go further and try to use these global warming potentials to multiply the tons of different gases that are being emitted. So for example, they might say that if you're emitting 100 tons of CO2 and 1 ton of methane, because methane has a GWP 100 of 32, then you've effectively emitted 132 tons of CO2 equivalent, so to speak. Because you've had the 100 of CO2 and the 1 times the 32 for methane. But you can see now why this has the makings of a lot of debate and controversy. Because when you choose to integrate the emissions over time, you lose a lot of detail. Who decides that 100 years is the important time frame? The warming due to methane is massively concentrated in the next decade or so, and tails off to nearly nothing towards the end of that 100 years. If what you're concerned about is temperature over the next 10 years, then 1 tonne of methane is much worse than 32 tonnes of CO2. But if what you're concerned about is the longer term, then it's not. But this is buried if you use the CO2 equivalent metric, which of course is integrated over time, and it's equating emissions from CO2 directly to some level of emissions from methane. On the other hand, some of these fluorinated gases can persist in the atmosphere for hundreds or even thousands of years. There are very few chemical processes that can naturally remove them. In this case, GWP 100 is ignoring the contribution to warming in subsequent centuries, so do we care about that or not? And how should we value it if we do? So if our goal is a certain temperature target by the end of the century, for example, then the methane we emit today is much less important than the CO2 we emit today. There's an argument, if the temperature in 2100 is what we really care about, that we should focus on cutting back on the CO2 quickly while allowing methane to be less prioritised, because the methane we emit today won't be affecting climate then, even though the CO2 still will be. And this, of course, is important because if you say that countries have to minimise their CO2 equivalent emissions, then they might focus on methane when actually we're arguing that we don't care about methane as much as we care about the other longer-lived greenhouse gases like CO2. This might all sound a little bit esoteric. Does it really matter if we get these exchange rates right when we should be focusing on cutting emissions of everything very quickly anyway? But it is important because of the conflicts that it can set up between different sectors in your economy and between different countries that have different types of economy. So, as we've said, the main culprit for methane is the agricultural sector. Now, if we choose an exchange rate that emphasises the importance of methane much more than CO2, then the pressure increases on agriculture to reduce its emissions. Maybe a lot of government funding and research effort goes into projects that can reduce or eliminate methane. Maybe in the case of a carbon tax, which is still one of the most commonly talked about policy techniques proposed to reduce greenhouse gas emissions, maybe then farmers are being taxed more extensively to reduce their methane emissions. Maybe when you do the calculating, it would be more important for people to reduce meat intake in their diets rather than driving more efficient cars or reducing the number of flights they take, and so on. And this is a problem when it comes to international agreements like the Paris Agreement. Under the Paris Agreement, countries are agreeing to limit their own emissions, and they're supposed to be ratcheting up ambition as we go along. The idea then is that each country is going to add some more ambitious goals, add some more ambitious targets. They'll look around and see what other people are doing and consider how they can bring themselves into line with that. But how can you judge what different countries' measures of success are when their economies are all different? Take a country like New Zealand, where a lot of cattle are raised and relatively little heavy industry shows up. Methane is around 45% of their greenhouse gas emissions in terms of global warming potential. In the US, it's just 10%. So a metric that emphasises methane unfairly compared to CO2 would put more pressure on New Zealand relative to the US to reduce its emissions. Ultimately, policymakers have to make decisions about what to focus on, what to prioritise, where to allocate funding, what to tax, and so on, if they want to meet their emissions goals. You can see then that the metric you choose to use to exchange between these different gases can end up being extremely important to how climate policy is actually shaped, even though these fiddly debates over how and for how long different gases contribute to global warming can seem quite esoteric. Recently, several scientists have been arguing for a new metric that treats methane differently. The reasons why are described in an op-ed written for Carbon Brief by Miles Allen, one of the authors of the paper. It essentially boils down to understanding how the climate responds to changing emissions of different greenhouse gases. If you stop emitting CO2 tomorrow, much of the CO2 you've emitted stayed in the atmosphere for centuries and continues to affect the climate. If you stop emitting methane tomorrow, the concentration of methane will fall over the next few decades, and that will actually cool the climate down relative to today. Similarly, if you emit methane at a constant rate, eventually the concentration of the gas in the atmosphere, and hence its impact on warming over a given time period, is going to start to stabilise as its decay into CO2 cancels out your emissions. On the other hand, if you emit CO2 into the atmosphere, it will continue to accumulate and continue to contribute to warming on the timescales we care about as humans. This non-equivalence has important consequences for how we mitigate. Because if carbon is taxed, if all greenhouse gas emissions are taxed by the same thing using global warming potential 100, it would unfairly penalise these short-lived emissions, assuming the aim is to penalise the contribution to warming. So he says, quote, "Consider a power station and a herd of cows. A power station emits CO2 by burning fossil fuels, and this CO2 is taxed. When it shuts down permanently, it emits no more CO2, so is no longer taxed. However, the CO2 already emitted continues to affect the climate for hundreds or potentially thousands of years. So even after closing down, that power station still contributes to holding up global temperatures because of the CO2 that remains in the atmosphere. Now the cows, a herd of cows emits methane, so the farmer is taxed for those emissions. If the herd remains the same size with the same methane emissions every year, it will maintain the same amount of additional methane in the atmosphere every year. In terms of its contribution to warming, this is equivalent to the closed power station. The power station pushed up global temperatures when it was running in the past, just as the farmer's great-grandparent pushed up global temperatures when they were building up the herd of cattle. But neither a steady herd of cattle nor a defunct power station is pushing up global temperatures anymore. However, under almost all proposed systems for taxing emissions that attempt to include methane, the farmer would get taxed for their herd's methane emissions every year while the cows were alive, while the owner of the closed power station would not. One way to make this fairer would be to tax greenhouse gases for every year that they remain in the atmosphere. Taxing all emissions since the start of the Industrial Revolution, however, may prove problematic. For example, how do we tax James Watt, the inventor of the steam engine, whose greenhouse gases still remain in the atmosphere today? Another way would be to use GWP star, the new metric, to calculate equivalent emissions, as this equates change in methane emission rates with tonnes of CO2. Thus, a stable emission of methane equates to a zero rate of CO2 emissions under GWP star, as it does not change the level of warming in the future, and would therefore not be taxed. The flip side of this is that any sustained increases in methane emissions would be heavily taxed, as they would contribute very substantially to future warming. Conversely, any sustained cuts would be rewarded for contributing to future cooling." End quote. And this type of argument also has consequences for our targets of net zero. Several countries, including the UK, have argued for net zero greenhouse gas emissions by 2050. But does this mean that each of our greenhouse gas emissions must be either zero or compensated for by removals? Or, for example, could we allow ourselves to emit some methane if we were scrubbing extra CO2 from the atmosphere, and therefore emitting that methane was contributing to warming, but that warming was being cancelled out by sucking CO2 out of the atmosphere, and so on. So as you can see, the ways in which we should prioritise emissions from different sources and different greenhouse gases remains controversial and debatable. Ultimately, the reality is that you're always going to lose some information by trying to come up with a way to directly compare different greenhouse gases. The exchange rate doesn't exist because it depends on what you care about. Clearly, when they have these different behaviours, in some ways it doesn't mean a lot to say that methane is many times more powerful as a greenhouse gas than CO2, without defining the time you care over, or whether you prioritise short-term warming or reversibility of climate change, or so on. At the same time, you need some metric for comparison to determine how you set your policies. So, when you pick a metric to compare emissions from greenhouse gases, be sure that you know what time frame you really care about. Thanks for listening to this episode of Climate 201. I hope it's given you more insight into the different greenhouse gases that are affecting the climate, the processes on Earth that cause them to be released, what a greenhouse gas actually is and how it influences the Earth's radiative balance, and the issues that we come up with for comparing them, deciding which ones to prioritise, and coming up with these exchange rates, and how these exchange rates in turn can influence climate policy. Remember, you can find the show at physicspodcast.com. You can send us emails, comments, questions, concerns on this episode. If there's anything that needs clarifying, let me know. You can send all that to the contact form, and I try and get back to people as soon as possible. You can follow us on Twitter at PhysicsPod. The Facebook page is Physical Attraction. We're always keen to see people there. You can support the show. We have a PayPal. We have a Patreon. The Patreon will give you access to past bonus episodes that we've made of the show. Of course, the best way to support the show is always sending me emails and also telling your friends who might be interested to listen to the show if you found it useful. Until next time, then, take care.
Thank you.